let's talk about double integrals. The notation of the double integral looks like this. So these two sling long s's, they're together. So this is one piece of the notation. Do not separate them. Okay, and the r here refers to the region that you integrate the function over with. Okay, and the a, okay, so this double integral notation and dA, they come together, so this is a set. Do not separate them. Okay, all right, so this notation means to integrate integrating the function f over the region R. Okay, and A stands for area element. So let me give you an idea. Okay, so this is x, y. Okay, suppose I have the xy plane. All right, I meant to draw it in a slant way. And then here I have a region R. Okay, could be this, could be rectangle. So I have a region R. All right, and I have function z equal to f of xy, right? So then if I sketch the graph of this function, then what I'm seeing would be a surface in general. All right, so now integrating f over the region R would mean what? Would mean that I only look at the part that is defined above the region R. Okay, and then so let me erase the part that's not necessary over the region R. So then then the board does not look too crazy. Okay, so only this is the part of the surface that's sitting right above the region R. All right, so this notation would mean that I partition the region R just like how we partition an interval. So I'm chopping this region into smaller, you can say rectangles. Okay, so for each rectangle it has its area. So let's say delta A. A refers to area and delta means this little piece. Okay, length of this little partition, just like the delta x in Calc 1. Okay, then I have like many small rectangles, right? And in each rectangle I'm gonna have a sample point. So I have a sample point. So let's say xi, yj. The I and j here are just index to tell you it's this rectangle, that rectangle. So it's just like index tell you which which rectangle we're looking at. Okay, so first partition the region R. So then we have small rectangles, and we can label them using I for x direction and using j for the y direction. Right. Okay, and then so therefore we have delta A, or you can say delta Aij to refer the area for each individual rectangle or each individual small region. Okay, so area. All right, I don't want to overwhelm you with notation, so I'm just saying delta A means the area for a little region, and 2 for each small region. We pick a simple point. Okay, so that I have a simple point. Okay, I don't care where you choose it, how you choose it. I just want this point to be sitting inside its corresponding small region. Okay, so with that, this simple point will give us a value f of xi, yj. Okay. So geometrically, this gives us the height of this point given by xi, yj, given by the simple point on the surface, right? Okay. So what does that tell us? So 3, when we use this value as a height. Okay, so here I have height times the delta area, delta A. What do I get? I would get the volume for this rectangular stick, right? Because I have a area times height, so I get volume. Okay, and the shape will be this rectangular stick, right? Okay, so I'm gonna repeat this process for each region of the partition, and then I sum over all these areas. Okay, so I sum over I and I sum over j. Okay, so what does this number mean geometrically then? This will mean like, okay, for each region I have an estimated volume, like maybe it's this over here for each one, right? That's over here, like that. Okay. So when I sum over this is the this gives me as an estimated volume. Volume of what? Volume of the solid under the surface and above the region R. Okay, so if I'm looking at this chunk, this is the surface over the region R. So here I get a solid. When I sum over these numbers, these volumes, what I get would be an estimated volume of this solid that we have. Okay, all right. So now the last, and this sum is called Riemann sum. Okay, so when I take the limit of this Riemann sum, okay, by chopping the partition, by taking the limit of the partitions. So what does that mean? This means I'm chopping this area finer and finer. So if I use the word resolution, I have higher and higher resolution. So after I take the limit, the limiting value, if the limiting value exists, this value would be how we define the double integral of function f over the region R. Okay? So therefore, by definition, when we write a double integral, we know that this is the volume of the solid under the surface given by z equal to f of xy over the region R. Okay, so that's what the double integral means and how it is being defined.